Okay, so this is lecture 13. We will continue on hexagonal lattices a little bit, followed by V zone law, and we will also see some effect of, finally we will see that although in a seemingly cubic lattice the directions may look similar, but symmetry may change that outcome completely. So, with that we will finish the Miller indices part. Okay. So, if I go to the next slide, so this is the recap of last lecture that we did. So, we have this hexagonal lattice, and within this hexagonal lattice you have this green colored smaller unit cell, which is the primitive unit cell of hexagonal unit cell, and then you for the sake of representation you can represent it as a hexagon which consists of 3 of these unit cells. So, in the normal unit cell you just need 3 axes. So, A1, A2 and C, these are the 3 axes you need. This is first axis you choose, there is the second axis you choose, and this is the third axis, the one which is perpendicular to the basal plane. So, 3 axis system is fine for a smaller unit cell, but when it comes to hexagonal representation, you see the problem arises because there are similar planes which are depicted in a different manner if you have if you continue with the 3 axis system. So, for example, as I showed you last time that and before I go into that, let me just tell you that HKL becomes HKIL with the condition H plus K is equal to minus I, and the direction capital U, capital V, capital W in 3 axis system becomes UVW, UVTW with the condition capital U plus is equal to 2U plus V, capital V is equal to 2V plus U, and capital W is equal to small w. This is very simple to do. You can just say capital U x hat plus capital V y hat plus capital W z hat, or rather A hat. So, you can say this is A1 hat, A2 hat, and this is C hat. This can be represented as U A1 hat plus V A2 hat plus T. Now, what is T? Is along A3, and A3 is minus of A1 hat plus minus of A2 hat plus WC hat. So, if we now do the matching of variables, matching of A, B components along A1, A2 and C axis. So, what you will get is, capital U is equal to, so if you just see this will be capital U will be U, and this will be minus of T. Capital V will be equal to small v minus T, and T is nothing but minus of U minus of V. So, this will become 2U plus V, and this will become 2V plus U, and W will remain as W. So, this is a very simple equivalence that you can set and determine what is UVW relations. Okay. So, now what I was coming to is that so in hexagonal system you have this plane, I think it is in the next slide. So, you have this plane, let us say A, B, C, D, and you have this another plane, let us say E, A, C, F. Okay. These two are equivalent planes, right. So, this plane is, you can say it is 1 0 0, this plane is 0 1 0. But if you want to now depict this plane, let us say this is G H. So, G E F H, this plane. If you go conventionally, this plane is nothing but the one which is diagonal in the smaller unit cell. So, you will say this plane is some sort of 110 type plane, right, because it has an intercept of it is you'll have to choose a different axis. So this will be 1 minus 10 or minus 110, okay. But in a 4 axis system, so in a 3 axis system it will become 1 bar 10, but in the 4 axis system this will become 10 bar 10, this will become 01 bar 10, and this will become 1 bar 100. So now they look as if they are family of planes, they are similar planes, and they are, so you can say that all of these are family of 10 bar 10 planes. So this will imply 10 bar 10, 01 bar 10, 1 bar 100, and so on and so forth, okay. So you will have 6 planes, all 6 planes, of course few of them are parallel to each other. So you will just change the negative signs and so on and so forth. So these are family of planes, that is why this 4 axis representation is better. So this is what I did to show you. Similarly, as I showed you, you can draw 1 bar 1 2 2 plane. So this is 1 bar 1, this is nothing but 1 bar 2 2 plane, 1 bar 2 2. What is the equivalence? Basically it is 1 1 2 plane. Now if you draw all such planes, let us say if you draw one from here to there, one from there to here, they may end up with different species. So if you just see 1 1 bar 2 2, this is first, the second one will become bar 2 1 1 2, and the third one will become 1 bar 2 1 2. Now try converting this in 3 axis system. This will be 1 1 2, this will be bar 2 1 2, and this will be 1 bar 2 2. So you can see that this is all right, but these two are different. So it gives you an impression as if they are different planes, because that is what we learned in cubic system or tetragonal system. 1 1 2 cubic system, 1 1 2 is equivalent to 2 1 2, and but here we see the planes which are identical in hexagonal system, they look differently in 3 coordinate system. So 1 2 1 bar 2 2, bar 2 1 2, and 1 1 2, they can be represented all by 1 1 bar 2 2, bar 2 1 1 2, 1 bar 2 1 2, and so on and so forth, okay. So this is not only true about this plane, but about the other planes as well. So I will show you a few more examples. Similarly about the directions. Now this is a projection of basal plane of hexagonal system, okay. So basically we are looking down the C axis and we are looking at AB plane, okay. So direction 1 2 0, as we know, we can draw 1 2 0 will be 1 2, there is no translation in C. So this is the direction. In the 3 coordinate system, this will become 4 coordinate system, it will become 0 1 bar 1 0. So if we draw this now, this will be 0. So 0, there is nothing along A1, there is 1 along A2, there is minus 1 along A3, and if you connect the final initial point, it is the same direction. Now this is again true of the directions. So all the directions of the kind 1 0 bar 1 0, 0 1 bar 1 0, 1 bar 1 0 0, and so on and so forth, all the directions will give you can see that what are these directions, okay. So one is this direction, another one would be that direction. So if you connect this point, if you connect for example that point, so on and so forth. Is that clear how to draw the direction in hexagonal 4 axis system? Now let us say if you have I am just thinking of what to give you. You can choose a little difficult example to work on. For example, how to draw 1 1 1 1 bar to 1 direction, for example. Okay. So this has all the 3 coordinates. So you shift the origin first of all, and so how will you draw that? 1 1 bar to 1. So you go 1 in A1, 1 in A2, and then -2 in A3, which means 1 and another 1. You will end up somewhere here, and then you need to go 1 up. So it will be 1 up in the C axis. So then you connect this point with that point, that will take you to, yeah. So as far as planes are so the 4 axis system has more advantage in terms of planes. The representation of planes is easier. In case of directions, you can live with, since direction is just a vector, you can draw them with the 3 axis system within the same system. But if you draw a bigger unit cell, hexagonal unit cell, then 4 axis system helps. Okay. So 1 1 bar 2 0 will be, you can convert this back to, so this will be basically 1 1 bar 2 0. So this will be nothing but, if you look at the direction 1 1 0, 1 1 0 direction is nothing but 1 1 bar 2 0 direction. 1 2 0 is 0 1 bar 1 0. So you will have to make the conversions. For example, so you have to use the formulas which I provided you for using small u is basically 1/3 of 2u minus v, small v is 1/3 of 2v minus u, small t is minus of u plus v. So you will need to make these conversions. So if you now convert back, so I said, so this is 1 1 bar 2, let's say 1 1 bar 2 0. What does 1 1 bar 2 0 convert into? So capital U was equal to 2u minus v. So this will become 2 minus 1 1. Sorry, 2u plus v, 2u plus v, I am sorry, 2u plus v. So this will become 3. Okay. V is equal to 2v plus u. This will become again 2 plus 1. This is 3, and w is w. So this direction will be 3 3, which is nothing but 1 1 0. So you could see that you go 1 step here, 1 step there, 2 step in this direction, which is nothing but the same vector. Okay, 1 1 0. So this is how you can make the conversions between the directions as well. Of course, if you draw it along the 3rd axis, it will become even complicated, but you can do these exercises at home. Is that clear? 3 and 4 axis system. So now I'll give you some more examples of hexagonal crystals. You have, so this is courtesy Professor Anand Subramaniam. He has made very nice slides on of these crystallography. So this is about, as I said, 1 1 bar 2 0 plane. So 1 1 bar 2 0 plane is nothing but 1 along x, 1 along A1, 1 along A2, and by default the 3rd intercept, which is -2, which is actually half, right? So intercept will be 1 1, as he has written, -half and infinity. All right. So it has a 1 intercept here, 1 intercept there, -half intercept along A3, and nothing along, and it's parallel to C axis. So you can see that this is the plane. So in 3D, the plane is going to look like that. So all the planes, so this is one kind of plane, this is another kind of plane, and you will have which is the other one, and the equivalence at the bottom. This will be another plane. Okay. So these are all identical plane, 1 1 bar 2 0, bar 2 1 1 0, 1 bar 2 1 0, and so on and so forth. Okay. So now this is the one I showed you, 1 0 0 plane example. So these planes are identical. This plane, that plane, they are identical. They look differently in 3 indices system, but they look same in 4 indices system. This is another example of plane which is 2 bar 1 bar 1 0. Okay. So 2 bar 1 bar 1 0 looks something like. Remember, you should always ensure in all these the sum of the indices is equal to 0. So 1 1 bar 2 0, sum of these 3 is 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 0. That equivalence must be maintained. If that equivalence is not maintained, then something is wrong somewhere. Okay. Here also we wrote this equivalence, this equivalence, this sum. So all the sums must be equal to HKI and UVT. These sums must be equal to 0. So it's obvious, but you might make a mistake. So just remember that. Okay. So this is this is the other plane that we have drawn, 2 bar 1 bar 1 0. This is 1 1 bar 2 0. So similar planes you can draw here, and this plane is nothing but parallel to this plane, right? The one which is here. Okay. This is 1 1 bar 2 1. It will look like that. The one on top 1 1 bar 2 1, and the one on the bottom is 1 0 bar 1 1, which is parallel to A2 axis. Okay. So basically this plane is nothing but 1 0 1 plane. Okay. But in 4D in 4 axis system it looks 1 0 bar 1 1. Okay. So 1 0 bar 1 1, bar 1 0 1 1, 0 bar 1 1 1, they are all similar planes. Okay. So this is about the planes and directions in various crystal systems. You have seen how we can draw the plane, how we can draw a direction, how we can identify a plane, how we can identify a direction, and we have also seen in cubic system that the direction lies perpendicular to the plane. Okay. So HKL direction is perpendicular to HKL plane, but that is only true of cubic system. In tetragonal orthorhombic it is only true for A, B, C axis, or 0 1 0, 1 0 0 and 1 1 0 direction. In tetragonal it is also true for 1 1 0, but not true for 1 0 1. Okay. So it is only true for certain directions in these systems depending upon the indices. In orthogonal system you still have some cases where perpendicularity is maintained, but in non-orthogonal systems it is not maintained at all. So in hexagonal system, for example, 0 0 1 direction is perpendicular to 0 0 1 plane, but that is the only direction which is perpendicular to 0 0 1 plane. So this relation is true only for cubic system. For hexagonal, tetragonal and orthorhombic it depends upon which direction and which plane are you talking about. Another crystallographic thing that you need to know is that Wies zone law. Wies zone law is basically, it is a very useful law, especially for plaster deformation, any phenomena that happens within the crystallographic planes where you need to know the anisotropy in the phenomena, and you need to find out which direction lies common to certain planes. So this law says that for a direction UVW lying in a plane HKL, the product of the dot product of the two H dot U plus K dot V plus L dot W is equal to 0. So this is called as Wies zone law. So basically what it means is that if you have multiple planes, right, all these multiple planes they intersect each other, and there is a common direction to these planes. This common direction is called as zone axis. This is of very much importance, especially in transmission electron microscopy when you do the diffraction patterns. In diffraction patterns what you will do is that when the electron hits the material along a certain axis, that may be a certain crystallographic direction. So all the planes which are containing that direction may be represented on the diffraction pattern. So sometimes there may be diffraction pattern spots from a few planes, and you need to identify, but using the Wies zone law you can identify which are the spots from one particular plane, which are the spots from other particular plane, because they must have a common zone axis. Okay. So this is of importance in transmission electron microscopy quite a bit. So if you have a direction UVW which is common to two planes H1 K1 L1 and H2 K2 L2, this is called as a zone axis, and it can be found as U is equal to, so basically you write two equations, H1 U plus K1 V plus L1 W equal to 0, and H2U plus K2V plus L2W, because it is a common axis, as a result it is common to both the planes. So, you can write these two equations, and these two equations can be solved in this fashion, right. So, U will be equal to, basically you can write U to be equal to K1 K2 L1 L2 and so on and so forth. You can write an expression for V, you can write an expression for W in the matrix form, and this will give you basically. So, U is equal to this, V will be equal to minus of H1 H2 L1 L2. Similarly, W will be equal to H1 H2 K1 K2, and you can see that U is equal to K1 L2 minus K2 L1, V is equal to minus of H1 L2 minus L2 H1. So, it will become L1 H2 minus L2 H1, and W is equal to H1 K2 minus K2 H1. So, that is how you can find the common axis between the two planes. So, you can see here, in this case you have, let us say, two planes, one plane is 0 1 0, another plane is bar 1 bar 1 0. So, you have a plane 1 0 0 and you have a plane 1 bar 1 0. I will go to the next slide probably, that will make it a little easier. So, you have a plane 1 bar 1 0 and you have a plane 1 0 0. So, for the first case it will become U minus V is equal to 0. For the second case it will become U is equal to 0. So, what you get here is, so let me just now draw a cube here, I think that is better, I think there is some mistake there. So, you take, this is x, y and z. Let us say you have a plane which is, so obviously from the examples you can also see what works and what does not work. So, this plane is 1 1 1 plane, right. What is this plane? So, if I choose this as the origin, there is an intercept of 1 along x, intercept of minus 1 along y. So, this becomes 1 1 bar 0. So, now if you have, so you can see that these two intersect each other, right. So, if they intersect each other, in that case, so in the first one also it is U minus V plus, so 1 minus 1 V plus 0 W is equal to 0, and the second one will become 1 U plus 0 V plus 0 W is equal to 0. So, in this case you can see that your U is equal to 0 and W is equal to 0, okay, which means V is equal to 0 and U is equal to 0, which means your W is undefined, we have not defined W here. So, the direction which is parallel to these two planes, which these two planes contain, is 0 0 W. 0 0 W direction will mean 0 0 1 direction, okay. So, both the planes will have 0 0 1 direction common. You can see that here, this is 1 0 0 plane, this is 1 0 0 plane, the plane which is drawn in red is, so this is 1 0 0 plane, this is 1 bar 1 0 plane, the one which is drawn in red. You can see this is the common direction, this one, and this direction is 0 0 1 direction. For the second case it is you have 1 1 1. So, U plus V plus W is equal to 0, and the first this becomes U minus V is equal to 0. You can see that in this case W is equal to 0, sorry 2U plus W is equal to 0 and U is equal to V. So, you can see that W is equal to minus of 2U. So, the direction would be u minus 2u. So, this is 1 1 by 2 direction. Okay. So, this is how you can find the common directions. Now, let me finally come to another point which is based on symmetry, that the set of direction is always related by symmetry. Okay. So, I will skip this slide, I will just go to the next slide. So, this is again courtesy Professor Anand Subramaniam. So, here you have a grid of points, right. You can see that in this case, if there is a four-fold rotation within the plane, then 1 0 0 1 direction is equivalent, 1 1 and bar 1 1 directions are equivalent. So, you can, if you rotate it by four-fold, you will get back to same configuration. So, this can be rotated by 90 degree, this can be rotated by 90 degree because there is a four-fold. Similarly, 0 1 is equivalent to 0 bar 1 because there is a two-fold axis which is present. Okay. Now, this is about when the motif is a simple single atom. Let us say if the motif becomes slightly different, if you don't have let us say in this case this is a rectangular lattice. If it is a rectangular lattice, then we do not have a four-fold there. This is what becomes in tetragonal system, right. In tetragonal system you have only one four-fold, others are two-fold. So, 1 0 0 is equivalent to 0 1 0, but it is not equivalent to 0 0 1. So, this is what is going to happen here. In this case 1 0 is not equivalent to 0 1 in the rectangular lattice. Okay. Is that clear? And similarly you can see what are the other families of directions. If you change the motif, you have a four-fold, but again there are no mirrors. If there are no mirrors, then the two directions which could be equivalent because of a mirror, they will not be same. Okay. So, for example, 1 2 and bar 1 2 do not belong to the same family. 1 2 and bar 1 2 do not belong to the same family because there is no mirror. Okay. So, symmetry changes the classification of direction quite dramatically. So, this is again an example where which directions are equivalent and which directions are not equivalent, it depends upon the type of motif. So, in a square motif, if you have a different motif, then also it changes, but in a non-square lattice with a simple motif, again things change. So, it depends upon the symmetry, whether you have four-fold present, whether you have two-fold present, whether you have mirror present or not, there is no mirror present. So, direction equivalence, the family of direction, the concept changes from system to system, which is determined by symmetry. Okay. So, to summarize, we have learnt about the direction u, v, w, which are Miller indices of a direction, which is nothing but a vector, and u, v, w in a triangular bracket is Miller indices of a family of symmetry related directions. So, since cubic is the most symmetric system, all of them happens to be of same type, but in tetragonal system they become different. Similarly, in HKL plane is a single plane, curl bracket HKL planes are family of symmetry related planes, and we do not typically allow separators in the Miller indices of directions and planes, they are written together. So, you do not write them as 1 space 2 space 3, you write them 1 2 3, okay, and unless of course the magnitude is in double digit. Okay. So, that is where we will finish this particular part. We now go to the next part, which is structure of metals. Okay.